And I'm showing here a comparison with 5 of the models that we have. And you can see here that they all have very different distributions. And only one of the models is able to simulate this bimodal distribution. This is the CAPS model. The other models, the reason why they can't simulate this distribution is because they do not maintain liquid in clouds at cold temperatures. And so this is one of the, I think one of the most important things we learned from Shiba was that liquid, you can have liquid in clouds down to -40 degrees Celsius. And you can see here that even now, these models, these state-of-the-art models, this lower left one is from the ECMWF IFS, the model that's used to create the ERA reanalyses. The middle and the lower one is the German Weather Service, DWD. So these are state-of-the-art forecast systems, still struggle to maintain liquid in clouds at cold temperatures. The other result I wanted to show, this is the scaled sensible heat fluxes on the y-axis. That's the 2-meter sensible heat flux divided by wind speed. And then again, the near surface stratification on the x-axis. And if you look at the upper left, this is the observations again from the flex stations. Each black dot is a 10-minute average, and the red is showing half-degree bins for the 3 different flex stations separately. That's why there are 3 dots in the vertical. And so another thing we learned during Shiba was that for very stably stratified atmospheres, the sensible heat fluxes begin to decrease, and then for very large stratification, they go to 0. And an intercomparison was done shortly after Shiba, showing that the regional climate models could not simulate this distribution. And this is a very interesting diagnostic because it shows the slope of this line tells you what the value of the transfer coefficient is in the bulk parameterization for the sensible heat fluxes. And so what they found with the intercomparison after Shiba was that people use constant transfer coefficients, meaning a constant slope, which meant that for large stratification, you had large fluxes. And the hypothesis was that's what prevented the models from being able to simulate very stratified cases. And so I just want to show one result here. So if you look at the CAPS model, the upper row in the middle, I showed that was the only model that could simulate the bimodal distribution in the previous slide. And you can see here the black dots, these are again the half-degree binned values from the CAPS model. And it does a really nice job of simulating this relationship for the cloudy skies, that's the negative stratification, and the positive sensible heat fluxes, down to about a 2-degree stratification. It is simulating the observed relationship really well. But what's really interesting, and the reason why it can is because these models, these bin models include the similarity functions that were developed using the observations from Shiba. But what's really interesting is that it still cannot simulate these very stably stratified cases, showing that there are other processes that are limiting the models from simulating that variability. So those are just a few of the preliminary results that we have, as well as some of the planned model studies and data sets that will be developed to use the MOSAiC observations to evaluate models.
Thanks very much, Amy. That's a great introduction to our discussion today. So I'm wondering if there are any general questions about Amy's talk before we listen to Marika's talk, and then we'll have a more general discussion. Are there any specific questions for Amy? You can go ahead and unmute and ask the question if you have a question. If not, we'll have our second presentation here is by Marika Holland. Marika is with the National Center for Atmospheric Research in Boulder, Colorado.
Thanks. So let me just get this started. Okay, so hopefully you can see my slides and you don't see the note version of the slides.
Yes.
So, great, thank you. Okay, so yeah, so thanks for the opportunity to share with you some of the work that we're doing and some of the plans that we have for model developments using MOSAiC observations. And so I'm representing the PROMISE project. So this stands for parameterizations for optics, mass, ice, and snow. And you can see the team here from our project, all the individuals that are involved. And we did have someone on every leg of the MOSAiC expedition. So that was very exciting, and we have a lot of great data to work with. So the three main questions that we're tackling under the context of this project is, what is the role of snow properties in controlling the sea ice mass balance and the early summer shortwave radiation budget? How is solar energy partitioned, and what is its fate in the seasonal ice system? And how is energy partitioned between basal and lateral melting? And what are the processes that affect the ice-ocean heat exchange? So those things were all designed because they represent important uncertainties in our coupled climate models. So this really is sort of targeted at understanding processes and improving sea ice components within coupled climate models. So I'm not going to go into any details really about the MOSAiC expedition. Rich covered this quite clearly in his introductory remarks, but you can see the track of the MOSAiC expedition here on the map. And of course, it occurred over a full year. So in terms of our particular project, there's several focus areas for model improvement that we're addressing. The treatment of albedo within sea ice models, snow processes and the heterogeneity of snow on top of sea ice, ocean heating and lateral melting. And all of these things we're considering within the thermodynamic treatment of the sea ice model CIRES. And more specifically in terms of CIRES within the community Earth system model. So this shows a schematic of the CIRES model in terms of its subgrid scale treatment. So each grid cell has 5 ice thickness categories and a single open water category. All of those ice thickness categories have different thicknesses, snow thickness on top of the sea ice, pond cover, aerosol content within the snow and ice, and heat and moisture exchanges with the atmosphere and the ocean. So we do have some representation of the heterogeneity of sea ice at a subgrid scale level. So in terms of the factors that we're trying to improve in the model, one of these is the treatment of the sea ice albedo. And within a category in the model, we can have 3 possible surface types. We can have bare ice, ponded ice, and snow-covered ice. And we do a different radiative transfer calculation for each of those surface types for each ice thickness category. So that can be a maximum of 15 different radiative transfer calculations. We use a Delta Eddington multiple scattering treatment for that radiative transfer. And in doing so, we prescribe inherent optical properties for snow, ponded, and bare ice, and also dust and black carbon. The radiative transfer is computed in 3 bands. So this shows the albedo as a function of wavelength here, from observations shown for bare ice in the red and ponded ice in the blue. And then you can see how the model would represent this in the black lines for these 3 different spectral bands. And then we do have some tuning knobs that allow us to go within plus or minus standard deviations from the observations. So there are some limitations in this treatment. One of them is that the optical properties, especially for the ponds, are based on relatively few observations. Another is that we don't include event-based changes, things like rain on snow events. So we have started with assessment of what our model actually simulates within the context of the MOSAiC observations. And so what I'm showing here on the left is the broadband albedo for CESM2 simulations in this kind of smooth line with the range across ensemble members in the blue shading. And then Shiba and MOSAiC observations shown in the symbols. And you can see that on the whole, the broadband albedo actually looks quite good in the model relative to the observations in terms of its seasonal evolution, its minimum albedo, et cetera. But we do have some indications that it's simulating a reasonable albedo, but for the wrong reasons. And you can see the indications of that on the right-hand slide, where we show the ponded fraction for the sea ice in the model in the kind of smooth blue and red lines, and then the observational ponded fraction in the symbols. So we're getting a reasonable ponded sea ice albedo, but with too many ponds on the sea ice in the model. So this suggests that perhaps our pond albedos are too high. Perhaps we have too much snow remaining on the sea ice in the summer within the climate model. And so we're digging into those things more carefully. But all of this is aided by the fact that we actually have great observations from MOSAiC that are allowing us to better characterize and understand things like the albedo of different surface types. So this is showing spectral albedos from MOSAiC of ponded ice. And you can see, so it's showing it from MOSAiC in green, IceScape in yellow, and Sheba in the orange colors. And you can see that there's this tremendous range in the albedo of ponded ice, depending on the pond characteristics, which is not something we currently incorporate very well in our models. There's other measurements that were taken at Sheba that are providing new opportunities to think about additional types of parameterizations. And so in particular, I'm showing some observations here of the spectral albedo from sediment-laden ice that were taken from June and July. And this is, again, something we don't include on our climate models, sediment-laden ice and the optical implications of that sediment-laden ice, but these observations from MOSAiC are giving us an opportunity to start thinking about how to parameterize that and parameterize the albedo impacts. Additionally, we have observations from MOSAiC that are providing information on the influence of specific events. So fresh snow events on a melting sea ice surface, shown here for the end of June, rain on snow events shown here at the end in middle of September. So these are the kinds of observations that we're using to think about albedo improvements in the model. And the targets that we have in the near term are things like increasing the number of spectral bands, updating our inherent optical properties, particularly for ponds on the surface of the ice, and also reassessing some of the assumptions that we have in terms of the factors that affect our surface types, in particular, the factors that affect ponding on the surface of the ice. Further out, we're also looking at the influence of these episodic events like rain on snow and also sediment in sea ice. Another aspect of our project is looking at snow on sea ice. So within the model treatment, the sea ice model has a single snow layer on each ice thickness category. But we know that the snow on sea ice is very heterogeneous. And so this is really not something that we represent very well. And we also have indications that this could be quite important for the sea ice mass budgets. So in particular, the distribution of snow has a very large impact on the effective thermal conductivity of that snow. And so sea ice growth in the winter months. The fractional coverage of snow also has a large impact on the surface albedo. And so the melting of the surface at the beginning of the melt season. So these are things that we don't adequately include in the model. And again, we have great observations from MOSAiC that are allowing us to better understand snow heterogeneity, the redistribution of snow, et cetera. So this shows some snow Lidar data. Lidar data was taken for the same region every couple weeks. This shows a scan from January 25th on the left. So this is showing surface topography. And basically what you can see is that in the blue, there are these areas of level ice. You can see these ridged ice areas in the kind of greenish and red colors here. And then on the middle panel plot, you can see the difference in that surface elevation between January 25th and February 4th. And over that time period, a snowfall event happened. So we can attribute these changes in the surface to snowfall on the sea ice, but you see that that snowfall is not at all equally distributed across the ice. And indeed, you see that there's a redistribution of that snowfall from level iced regions to along the sides of the ridges. And so we can start to quantify that, shown here on the right in a PDF of that surface height change. So these are the kinds of data that we're using to better understand the heterogeneity in snow conditions, redistribution of snow across the surface of the sea ice, and then looking at the implications of that for sea ice mass budgets. So in terms of model parameterizations, in terms of snow heterogeneity, we're revisiting things like the effective thermal conductivity of snow to better account for this heterogeneity. And we're also revisiting the snow patchiness, what we have called patchiness in the climate model, which is the fractional coverage of snow on the surface of the sea ice, which currently is just a simple function of the snow thickness. So those are the kind of processes that we're considering in terms of model improvement. And then finally, I just want to very briefly touch on the fact that we're also looking at ocean heating and lateral melting within the model. So currently in the model, lateral melting is a function of the ocean heat in the first model layer within the ocean model. The function that we use for this is based on very few measurements. And so there is an opportunity to improve that functional form. There's also the opportunity to change how our treatment of leads within the model. So currently, our ocean models don't really resolve leads. They don't resolve that you have water embedded within the ice, essentially. And we do have observations from MOSAiC, shown here on the right, that shows that these leads can become very stably stratified as meltwater is entering them, and that can allow heat to accumulate in the upper meter or so of the leads, where it can very directly impact lateral melting. So we're thinking about these processes as well and how to better incorporate them into our coupled climate models. So that was just very brief information on the work that we're doing under the PROMISE project. And so it includes these studies of ice albedo, snow processes, and leads. And we are targeting model developments in all of these areas. In the near term, though, those improvements will be targeted at the surface albedo and in particular ponding on the surface of the sea ice. But we are also looking at these other impacts of snow heterogeneity and lead heating and lateral melting. So I'm happy to take questions or move into the general discussion. And I also note that there's multiple PROMISE team members on the call. So so they might chime in too with answers if needed.
Thanks, Marika. Okay, so I have a question or two for both of the speakers. Marika, so in comparing the CESM to the historical observational record from MOSAiC, are you looking at the time averaged fields for evaluating against observations, or do you have is there a single column version of the ice model for looking at the sea ice, or how do you do the comparison?
So far what we're doing, and I'll stop sharing my screen unless there's a reason to keep sharing it. Okay.
Yeah, go ahead.
Just because then I can see people.
Yeah, that's good.
So far we're just actually looking at coupled climate model simulations, taking out basically a grid point in the vicinity of the MOSAiC field campaign and looking at that kind of for a rough assessment in terms of what the coupled climate model is simulating. So we are doing that for individual years and then looking at the range around that using different ensemble members, say, or different years of the simulation. So it's basically a way to get a sense of, is the model doing things and is it doing things for the right reason? We would love to have a single column version of CICE forced with MOSAiC observations. And we have had some conversations with others in the CICE consortium about trying to develop that capability because I think that would be a great test bed to look at things much more directly, and in terms of the events that happen during MOSAiC and how a sea ice model simulates those events, but we don't have that currently.
So you did touch on Shiba. Is it for the types of comparisons that you are going to do? Is it useful then to have 2-year-long field studies in different conditions then for evaluating the model?
Yes, I think it is. I mean, they're in different locations. They, were subject to different weather, events, et cetera, et cetera. And so I think in terms of understanding those, and they also occurred at very different times, you know, I mean, in terms of decades different in terms of, so their timing. So I think we are kind of looking at all of those things, like how these things actually change in our climate model over the decades, and you know, spatially as well, in the Beaufort Sea versus the MOSAiC drift region. So yeah, I think it's very valuable to have these 2-year-long drifts.
Okay. And okay, so going back to our first speaker, Amy, you also touched briefly on the Sheba results and the supercooled cloud liquid water. Do you think that, what question should I ask here? Do you think that the models then have advanced since Sheba in trying to address this, and that, well, I guess, and I'm just thinking of our model development. We've tried 2-moment cloud microphysics and have had a lot of difficulty in implementing that for the Arctic. So do you think that, you know, we essentially tried to develop something from Sheba, and then we've gotten into some difficulties, and that MOSAiC offers an opportunity for additional observations to try to resolve what those difficulties are?
We'll see. I mean, there's one limitation to the MOSAiC observations in that it's not clear that we have the right aerosol measurements that we need to improve the parameterizations of the ice nucleation. So, and that's really what this is all about, is limiting the production of ice. And so that's yet to be seen. I mean, that's our hope, is that we can use these MOSAiC observations to improve those parameterizations. And all of the different forecast centers have sent me their the way that they're parameterizing ice and liquid in clouds. And so we'll start looking at that, and that's the hope. But most of the observations were taken at the surface, and it's not really clear if that's sufficient to be able to constrain the parameterizations of the microphysics. But that's definitely our hope.
Okay, that was going to be my second question, because MOSAiC was, I think there were anomalous aerosol conditions associated with high latitude forest fires and things like that in the Arctic. So I was kind of wondering about the aerosol observation availability.
Yeah, actually MOSAiC was anomalous in a lot of different ways. I mean, there was a very strong polar vortex, and the winds were very strong, and the ice was moving a lot faster than they had anticipated. So it's going to be a challenge to try to extrapolate to more general conditions from the MOSAiC year in all of these things, the aerosols, the circulation.
Okay. Okay, I think we'll start with some general questions for each of the speakers. I see a few questions have been asked in the chat here. The first one was from Mike Steele. Marika, isn't IcePack a single column ice model?
Yeah, so, yep. So, and Dave then mentioned, kind of responded to Mike Steele's question within the chat as well. And then I responded to Dave's comment. So yes, IcePack is a single column ice model. IcePack is basically the thermodynamic, the single column physics from the CIRES model. And so the plan, the hope, is to have an IcePack case that is forced with MOSAiC observations, you know, so we can actually have it driven by what actually happened at MOSAiC, and then we can use IcePack to look at processes, you know, comparisons to the expedition data, you know, all of that. But yes, it would be within the context of using IcePack.
Okay, Bjorn, do you just want to unmute and ask your question?
Yes, okay.
Yeah, hello.
Thank you. I was just wondering, those measurements of albedo and radiative fluxes, and I was just thinking and asking, have you made any assessments of what is the latent heat forcing, so to say, of the fluctuation in albedo in terms of centimeters melting or growth of sea ice?
in terms of the variations in
Yes,
albedo.
the drivers or the albedo fluctuation forcing of the heat transfer both ways. Is it what would it be if you transferred it over to centimeters of ice, either growth or melting?
Yeah.
Ice formation, the growth is more or less in ridging and drafting. Have you any numbers of that? And or what is it in watts per square meter to begin with? Thank you.
Yeah, so I don't have those numbers right offhand, although I think they're quite easy to get, and maybe someone else has those numbers on the call. I will say one of the important things about these variations in the albedo is that they can integrate through the entire melt season. So it's not just the instantaneous variation that's important, but the fact that it has this integrated influence over the entire summer melt season. So its effect can be larger than you would otherwise guess. But I don't know if anybody else wants to provide some numbers. I mean, I think we could. I see.
No, my argument is to think about the ice growth and decay. What does it transfer, or how does it transfer over to ice thickness? Yes, just a curiosity. Thank you.
Yeah, I mean, I think it does have a big impact on the ice thickness. And, you know, if that albedo change is in June, say, when the sun is at its peak, it's, again, first it integrates through the entire melt season, but it also has a very large watt per meter influence immediately. So the timing of those albedo changes over the seasonal evolution is also really important, in part because you have such a large annual cycle in the shortwave, the incoming shortwave radiation.
Holland, you have your hand raised. Do you want to unmute and ask your question?
Yeah, thank you. Yeah, thank you to both speakers. Very interesting results. So I have a specific question for Amy about the analysis on the joint PDF between surface net non-wave and the temperature difference. So those are for all skies, right?
Yes.
So is the dipole structure one for clear sky, one for cloudy, or I'm just trying to understand the results.
Yeah, that observations show that in the Arctic there are preferred either clear or cloudy. There are very few cases in between of that is either, and that this bimodal distribution is very difficult to simulate, mostly because the models don't have a cloudy mode. Okay, I see. But you do have separate measurements, like you can identify when is cloudy and when is clear. If we want, you can separate them out, right? Yes, and I've done that. I've definitely done that. Okay. And I do have a general question. So for those currently, those analyses you're comparing numerical weather prediction models or analysis or real analysis. Do you have a plan or anyone else on the team coordinating a model, global model intercomparison or regional model intercomparison activity? Our work is focused on the forecast systems. Okay. Okay, maybe I will pay attention to other people's work. By the way, we're very interested in participating in this kind of analysis and model comparison in order to evaluate our model and improve our model. Thank you.
Thanks, Alan. I'm not going to say this name right. Helge Gössling?
Yeah, hi, thanks. This is Helge Gössling from Alfred Wegener Institute. So yeah, thanks for these two excellent talks. So I just wanted to touch on this sea ice column modeling theme. So within this YOPP sea ice task team, we have actually also, we are considering this one of the big things that will be very valuable in order to make the best out of the MOSAiC observations for sea ice model development. And so as part of that, we kind of started to put together or get together a group of anyone interested in doing such a thing. And we had recently one of the IcePack developers also presenting in our task team meeting. And Frank Kauka, actually, so he's kind of starting to coordinate that, and he and a colleague and another colleague at Alfred Wegener Institute, they have been doing something already also with IcePack in that context. And so I think in that regard, it would be very important to really to talk. And actually, I guess, I mean, Marika, I think, and Amy, you will, I'm sure you will agree, actually, Amy and I, we are co-leading this task team. I think it would also be great to have you talking, giving a similar talk in that task team meeting, one of the upcoming ones. So I think that's really, you are very far already with what you already do with the MOSAiC data for CIRES model development, I believe. Yeah, so that basically that's what I wanted to say. Thank you.
Thanks. I guess to add to that, I mean, we've been trying to develop a single column version of our numerical weather prediction model for understanding the clouds. If there was a intercomparison of the atmospheric single column model, would probably be more motivated to get our single column model in better shape for intercomparison. So I don't know if there are any thoughts on that, but that could be an interesting activity for the future. Okay, I see another comment from Shengdong Zhang. Do you want to unmute and ask your question?
Oh, hi, it's Xiangdong. Okay. Yeah, my question is to Marika. So hi, Marika. So you presented the spectral dependence of the albedo. That's quite interesting, you know. So I'm wondering when you develop a new albedo, the improve the albedo treatment in the model. So how broad the spectral band that albedo scheme can cover? You know, there is a larger difference, right, for different bands, spectral band. I cannot hear you.
Sorry, muted myself.
Oh, yeah, okay.
So I'm trying to remember exactly how far our spectral band goes. And I'm not sure if Bonnie or Dave have what the actual range is in our spectral band.
Okay. Yeah, it seems like you currently use a two-stream scheme, right? So if there are any changes from there?
No, I don't. So we're not really targeting a change in the radiative transfer treatment itself, but in the inherent optical properties that we're using within the radiative transfer treatment. We are talking about possibly increasing the number of spectral bands within the context of the Delta Eddington scheme. Yeah.
Okay, I see. Yeah, yeah, that would be very interesting. So actually, I have one other question about the IcePack model, the ice column model. So when you develop or get a new ice column model, so how is there also thickness distribution in that model to be considered?
Yes. So the IcePack model is all the column physics, including the ice thickness distribution.
Okay.
And so you do need mechanical forcing to drive the model, because you need to have the forcing that will allow the model to produce ridging and ice divergence. Otherwise, your thickness distribution will fall.
So considering the basal and the lateral melting, so what's the treatment of the ocean part for this IcePack model?
So we often run it with a slab ocean model. So basically just a heat reservoir that, so it with a single temperature.
Oh, I see.
So it does have surface exchange that can influence the ocean heat, but you don't have any, ocean dynamical processes.
Okay. just an energy balance ocean mixed layer model, something like that, right? The slab model.
It's even simpler than I think it's a stretch to call it a mixed layer model. I mean, it's just
Okay.
it's a single equation for temperature.
Single equation, yeah.
That it, reacts to ocean, to surface exchange and.
Okay, yeah. Actually, I have one more question. Is it okay? I have one more question.
Go ahead.
Okay, one more question to Amy. So Amy, you show the fully coupled model using the MOSAiC data to verify, to validate or comparison. So I know that there is Arctic codex. So is there any also the modern experiments using atmosphere only model to make a comparison with the observation from a MOSAiC, or just for couple model, fully coupled model?
Each of the models has a different degree of coupling. So some are just coupled ice and atmosphere, and some are ocean, ice, and atmosphere. We're trying to use as many include as many of the models as we can. But there really aren't any atmosphere alone comparisons planned at this time, because we're really interested in the exchange of energy through the whole coupled system. We feel like that's sort of a new way to evaluate these systems compared to what was done for Shiba.
I see. Okay. I know there are some modern experiments finished for Codex project for the Arctic region model. So after MOSAiC experiments, is there any plan to organize a similar rerun model to include MOSAiC observation?
For Cortex? For Cortex?
Yeah.
We're not really working with the Cortex community right now, but that's a really excellent idea. I think that will be done.
Okay. Yeah, thank you. Yeah, both are excellent presentation today. I like that. Thank you.
Thanks.
I have an answer if you're curious about the actual bands, but so we do visible and so-called near infrared, and we do direct and diffuse for that. So we have the 4 sort of categories for that. And then the near infrared is basically up to 5 microns, is where the upper limit of the near infrared is. So.
Okay, thanks, Dan.
Okay, we have about 10 minutes remaining. I think in my invite at the beginning of the month, I asked if anyone else was doing work using MOSAiC data for modeling analysis. And I was just kind of wondering if anyone else has their own story about using MOSAiC data or their plans for using MOSAiC data. Does anyone else want to speak to that? I guess I can speak for myself first of all. I think the GMAO has been a little bit slow about evaluating our numerical weather prediction against the MOSAiC data, but I think we want to do that. We have it all archived. One of the issues was we changed model versions for our numerical weather prediction in the middle of MOSAiC. So, but I do think that we want to go back and compare what we predicted versus the available observations.
I would say that it's on our agenda, but we haven't started. But those results already showing here very promising and interesting. But I did have some experience with using a different field campaign called NICE, pretty early years. And we try to use very fine resolution regional model, polar WRF, to simulate. It's very challenging to get clouds right. Even if you look at we use the reanalysis error 5 or error 8 interim to drive. You look at the meteorological conditions, they're very close to sounding, but if there's a little bit of time lag, then everything is screwed. Especially when you have a cold front or a small scale system passing the ship, then it's really hard. So I'm actually very impressed when some of the model actually can capture those statistics pretty well, but event-based probably even harder. So I don't know if it's a good idea to design some simpler activities for global models. We don't expect that the coupled model can actually get everything right. Maybe can get one thing right and then screw the other parts. Probably nice to dissect those processes.
Thanks, Alan.
Yeah.
Any other comments?
Yeah, may I a little bit?
Sure.
I'm kind of missing out a little bit of what is done in MOSAiC in terms of ice kinematics, deformations in the ice and thickness redistribution. And that's because I'm coming from the ice mechanics. But all studies in the ice kinematics, they have a bearing on the, at the end of the day, to the planetary boundary layer, what the vertical flux of horizontal momentum, the forcing, and also the sea surface tilt. So I'm very excited to see studies on the atmospheric friction or the momentum flux, horizontal momentum flux in vertical direction. So does anybody have comments on that in this group? Thank you.
I don't.
Well, this may not be the right crowd because there's nobody talking about ice kinematics or ice reaching and drafting here. So maybe that's in another forum. I don't know, but it must be a part of the modeling. And
That's true. I noticed a lot of participation from the CICE leads, or I did. I think they've dropped off the line, but maybe this could be. But maybe that could be addressed in another meeting. I do know that there was a lot of modeling done to try to forecast the drift of the polar stern. So, I mean, that involves the kinematics as well. So,
yeah, I can maybe comment on that because that's the sea ice drift forecast experiment. I suppose you relate to, right?
yes.
Yeah. So that has been going on for the whole time of MOSAiC, and that was actually also one of these like special experimental products that we provided, because we collected, and actually we still collect for the remnants of the second flow that Polarstern was tied to, which is still like close to Greenland now, going toward Farm Strait, and there are still high resolution satellite images being ordered for the remnants of that second flow. And so we are still providing near real-time forecasts for that. And that means what we are doing is we are collecting from operational forecast centers that do have dynamic sea ice in their systems. So they send in near real-time trajectories that are based, so they put diagnostic tracers into the sea ice drift they have in their systems. By the way, Amy is one of the people contributing that in near real-time every day. And then we are kind of centrally putting them all together and construct a consensus forecast on the fly, so to speak. And that is then always made available. And indeed, what we want to do is evaluate a lot all that huge data set. We have it not only for Polarstern, for the MOSAiC drift, but also for quite a number of buoys distributed over the Arctic. And also the other thing, and that also relates to the kinematics, there's this a really extensive array of GPS buoys that has been distributed with this distributed network around the central observatory. And based on that, there will be a lot of study of the kinematics, and also in this SITFAX exercise, we also targeted some of those buoys of the distributed network. And what we want to do now is also to look, I didn't get to that point yet, but we want to look at how well actually the forecast systems on that spatial scale, so that is about 80 kilometers in diameter, if the deformation that comes out of the system has anything to do with reality. So that will be very interesting.
That's great, thanks.
Thank you very much.
Okay, so I think we're coming up to the top of the hour. I just want to check in with my co-lead Wilbert. So I think for announcements for the modeling sub-team for next month. So we have a performance element that asks us to survey available modeling assets for the Arctic. And so to accomplish that, we're going to have a couple of roundtables, one involving program managers and the other one involving modeling centers. Mm-hmm. And I think the modeling centers goes first, right? That's on May 27th. And Marika and others will be presenting for that.
That's correct. Yeah, it's going to be a very exciting two subsequent meetings. Yeah, there's going to be of interest for a lot of people on this call, I believe.
Okay. Okay, I think that's going to wrap it up. I thought this was a very good meeting. Thanks very much to the two presenters, Marika Holland and Amy Solomon. And I think that concludes the meeting. Thanks very much.
Thanks, everybody.
Thank you very much.
Thank you.
Bye-bye.